Hello, my eager math students. This is Miss Auk, and we begin Math 30-1 today. First unit we're going to do is functions and relations, and that's important because so many of our units in Math 30-1 involve functions, so we're going to start off by reviewing some functions. In particular, we're going to be looking at polynomial functions, cubic, quadratic, linear, and absolute value functions, radical functions, and then we'll look a little bit at some function notation. This first video will probably involve the polynomial functions only. So first of all, polynomial functions, what are they? Well, here's sort of a mathematical definition of polynomial function. It looks horrible, doesn't it? But if you look down here, this is really just an example of a polynomial functions. One of the conditions it has to be true is the leading coefficients, or sorry, not the leading coefficients, the coefficients in front of each term have to be real numbers. So no square rooting a negative number. And the other condition it must hold is n, which as we see up here, is the exponent on our variable. And that has to be a whole number. Numbers like 0, 1, 2, yada yada. Okay, so if we look, then we've got all that. The degree of the polynomial, we need to know what that is. The degree of the polynomial is the exponent on the highest, or the highest exponent on one of the terms in the polynomial. So if we look at this example here, we have this term here has the highest exponent of 4. So therefore that is our degree of our polynomial. The leading coefficient is the coefficient in front of the highest degree term. So if you look, the number in front of x to the 4, well, it doesn't appear to be 1, but it's assumed to be a 1. So therefore our leading coefficient is 1. It is not the 7, it has to be the coefficient in front of the highest degree term. All right, now the constant term is really the term without any x at all. So if you look at these 4 terms, the one that doesn't have x, that's the positive 5. So our constant term is 5. And remember, the sign in front of the term goes with the term. Okay, so let's take a look at linear functions. A linear function is a polynomial function of degree 1. So the exponent on x is a 1. And it's quite often in this form, f of x equals ax plus b, where b is your y-intercept, and a, sometimes called m, is your slope, which is rise over run. And this will produce a straight line. The graph is a straight line. Another function whose graph is a straight line is a constant function. And just as the name implies, it's a function that never changes. It stays constant. So the y value stays constant. The exponent on x is a 0, therefore degree 0 for a polynomial function. And it might be an equation like f of x equals a. Okay, let's take a look at example number 1. So first one, y equals 3x plus 1. Oh, look at that. We have an exponent of 1 on our x, which means it's degree 1 and it should be a straight line. So if we use the old y equals mx plus b to graph this, we start with our y-intercept, which should be 1. So we'll call this 1 here. We'll have a slope of 3, and I'm going to make that 3 over 1 so that we can see the rise would be 3 and the run would be 1. So up from our y-intercept we go up 3 and then over 1, and we're somewhere in there. And now we should be able to draw sort of a straight line through there. Hopefully yours looks better than mine. And there's our graph. Now they're asking for the domain. Domain is really all possible values of x on this line. So if we look, with this point here could have that value of x, this one could have this one, over here we'd have this value of x. Really it ends up being every single point on that x-axis, which means in set notation our domain would be x such that x is an element of the real number system, meaning all real numbers. Now let's look at range. Range, we're referring to the y value, or the dependent variable. And if we look at this graph, we have Could have a y value here, one here, one here, one here. Looks like it's going forever up and down. So we actually have all these y values. So again, just like for the domain, y such that y is an element of the real number system. Okay, next example, y equals 5. We're missing an x, aren't we? That must be a constant function. So we are going to, let's see, y equals 5. Well, I know y equals 5 here on our y-axis. Let's think of another point that would have a y-coordinate of 5, like let's say 3, 5. I see a trend here, -2, 5. This line is going to be a horizontal line crossing the y-axis at 5. Okay, let's take a look at the domain for this one. So domain, okay, let's look at this next example, y equals 5. All right, notice there's no x there. So, no x, that must be a constant function. Okay, still a straight line, but it's a special one. Let's think about on our graph. Where would y equals 5? Well, we know on the y-axis here, that's where y equals 5. Where else would it be? Let's say we have a point 3, 5. That might be over here somewhere. Or -2, 5 might be over here somewhere. Okay, it looks like our constant function is going to be a horizontal line, and that would be the case with all constant functions. All right, let's look at domain. Well, once again, looks like we have all these x values, so x would be an element of the real numbers. And range, oh, a little bit trickier. If you kind of look from bottom to top, really the only value of y we have on this graph is 5. So we're going to say y such that y equals 5. It's our only value. All right, next example, let's look at quadratic functions. So quadratic function is really just a polynomial function that has degree 2, and it can be written in general or standard form. And you did this last year in 20-1. So the general form looks like this, f of x equals ax squared plus bx plus c, where a can't equal 0. Of course it can't, because if a was 0, that term would be gone, and it would no longer be a quadratic function. Okay, standard form. Okay, that looks familiar too. F of x equals a bracket x minus b squared plus q. That also gives us our vertex. The p and q is our vertex. Okay, let's look at this example. Use a graphing calculator to sketch the graph of the function with the equation y equals. Okay, we're going to need our graphing calculator. So you grab yours, I'll grab mine. Okay, here we go. So we are going to graph that on our graphing calculator. Okay, so we hit y equals, and we're going to put in that equation, x squared minus, you're probably a lot faster at this than I am, 3x minus 18. Okay, so we've got the equation in there. We're going to try with standard window settings first. We're going to hit graph and see what it looks like, but we may have to adjust. Oh, okay. You know what? I had already adjusted. But if you were in Zoom Standard, which is probably what you were in, then you would have gotten this graph. Okay. Now you'll notice we can't see the bottom of the graph. So what we're going to do is we're going to go to Windows, and we're going to change our y min to something smaller so that we can actually see the bottom of the graph. Make sure you hit a negative sign, not the minus sign in front of this, otherwise it may not work. And we're going to go not negative 256. Let's go negative 25. That should work. Okay, let's hit graph. There we go. We can see the entire parabola. Okay, first off, we need to find the zeros of the function. So zeros are the x-intercepts. Sometimes you can get those from the table, like you'll see this one showing up over here. When x is 6, y is 0. That's a 0. Okay, and we're going to write that one down. And the other one we're going to find, which we could get from the table too if it was an integer, but we're going to find it using the second calc feature on the calculator. So we need to go second calc. Okay, pick 0, number 2, And for left bound, we want to be left of where we think it is. So we're going to cursor left arrow till we're left of where we think it is. That looks good. Okay, now we go right of where we think it is, hit enter. And for guess, really you don't have to move. You can just hit enter again. And there we go. We have -3, 0 is our other 0. Okay, we could find the 6, 0 the same way. They want the y-intercept. Well, one thing we know about y-intercepts, x is 0. So, good way to do that is to hit the trace button, or you can do second calc value. And if you just type in 0 for x and hit enter, you get -18. There's our y-intercept. Okay, now coordinates of the vertex. Okay, the vertex is either the very bottom of this parabola or the very top if it's opening down. So to get that vertex, in our case, it's going to be minimum. So we go second calc, minimum, number 3. Okay, left of it. Again, I think we're left of where it is, so that's all good. Let's hit enter. Now we want to move with our arrow over to the right till we think we're right of it. Yeah, one more. There we go. We should be there. Hit enter, and again, for guess, just hit enter again. Calculator will find it. All right, so our vertex, that 1.49999, that's basically 1.5. And our y coordinate, -20.25. All right, and finally they want us to find the domain and range. So if we know that vertex point, then we know the lowest value that y can be. So we're going to use that to do our domain and range. So back to our page, we'll record some of this information now. The zeros, as we discovered, were written as coordinates would be -3, 0, and 6, 0. The y-intercept we discovered was 0, -18. Coordinates of vertex were 1.5, -20.25. Okay, and our graph looked something like this. Okay, domain and range, therefore. Okay, now if you look at all possible values of x on this graph, it goes forever left and forever right. So again, x such that x would be nominal reals. Range, really, we've got to be higher than this vertex point, and we knew that that was -20.25. So y such that y has to be greater than or equal to -20.25. And there we go. We have our domain and range. Now use factoring to determine the zeros. We're going to factor this. So zeros means we set y to 0. So in our equation, we would put 0 equals x squared minus 3x minus 18. And we are going to factor that. And if you're a little rusty on factoring, check out the factoring video to refresh. So x squared. So there is no greatest common factor, so we wouldn't worry about that first step. X times x gives us x squared. We need to multiply to -18, add to -3. So that's going to be -6, +3. And then we set each factor equal to 0 to find our zeros. Okay, so isolating x would equal 6. And x equals, subtract 3 from both sides, x equals -3. There you go, same zeros we got when we graphed it on the calculator. All right, rewrite the equation in standard form. So we, for the sake of time, are going to skip that particular portion. And we're going to go to example 3. Use graphing calculator to sketch the graph. Okay, you're going to find those, you can find the zeros of that, but what we're going to do most importantly on this example, again for the sake of time, is to use the quadratic formula to determine the exact values. So, quadratic formula, it is on your formula sheet, so please check that out, is basically -b plus or minus the root of b squared minus 4ac all over 2a, where a would be -3, b is 4, and c is 1. Alright, let's sub that in. Okay, we got subbed that in and got it simplified to this, but they want the simplest radical form. So we need to simplify that radical into 2 root 7. And then I would reduce negative 4, 2, and negative 6, followed by 2, so we would finally get negative 2 plus or minus 2 root 7 over negative 3. Let's change all those signs so they're positive. And there we go. That would be your exact value.